I am a soft matter person who does theory and simulations. So what I'm going to be talking about is simulating soft matter systems. Now, the first and foremost disclaimer is that one presentation or one thing is it's just not possible to cover everything, right? But we will see. I mean, we'll just give you a brief overview of how you try to simulate, what are the things that you take care of, and I'm going to illustrate with some examples from my own work that where you have to be careful, what kind of thermostats or integrators you have to choose, so on and so forth, right? Now, this is the middle world that we are looking at, and you have lots of examples. By now, you must be familiar with all of this. You have polymers, biomachines, membranes. That's the one that we have been focusing on so far. Colloids, cells and biopolymers, emulsions, biomachines, all of this. Now, what is interesting about all of this is that what distinguishes them from a matter which is hard like this is compared to what when you press your skin, it deforms. But if you press the table, it doesn't deform that easily because the energy scale for soft matter system is always of the order of kBt, right? And it's characteristic of all soft matter systems. As physicists and particularly people, theoreticians who like to model, our first and we love to coarse grain. So all of these blobs that you see over here, all of this have really very detailed microstructures. I mean, chemically, if you look at it, they have a lot of microstructures, but we are not interested in these microstructures. We are rather would like to see if there is some kind of universality that comes up, some kind of robust modeling that we can do, right? I mean, in chemistry, you will probably see that you can change this, the bonds, you can change the elements, and you will have something different, but the physical behavior, the overall collective dynamics would probably remain the same. And what we are interested in is this cooperative mechanism in such soft matter systems. So as the joke goes that we are always interested in a spherical chicken in a spherical world, I mean three-dimensional world, so that's how we always love to coarse grain, right? Now, molecular dynamics or simulations in general uses extensively what is called the principles of statistical mechanics. Whenever you start doing the simulations, you must have your stat make absolutely correct. Why is that? Because essentially you're looking at an n particle system, right? N can be very large or moderate or very small. I mean, but so once you look at n particle systems, you must be thinking about, then the question comes in mapping with the experimental conditions, right? Most of the experimental conditions are most likely open systems or systems which are kept at a constant pressure, right? So therefore, choosing the ensembles is extremely important in your simulation. The microcanonical ensembles that mostly used are NVE, which is the constant particle number, constant volume, and constant energy. And the corresponding one is constant particle number, pressure, and the enthalpy is the conserved quantity here, right? Now, the counterpart, the canonical counterpart to an NVE ensemble is an NVT ensemble, where basically you have attached a thermostat to the system and kept the temperature constant. So here, what you will see over here is if you measure if you do an NVE simulation, the particle number remains constant, the volume remains constant, and if your integrator is correct, then your energy should also remain flat. What will fluctuate is the temperature. On the other hand, in an NVT ensemble, you will see that the temperature will absolutely remain, well, within 1 by square root of n, it is going to remain constant, but its volume is going to fluctuate. Now, thermodynamics, of course, deals with these macroscopic quantities. Thermodynamics doesn't care about fluctuations. The fluctuations come in statistical mechanics. So if you measure these fluctuations, you can measure some of the material properties of the system. For example, in an NPH ensemble, or if I measure the volume, see, in an NPH ensemble, the pressure is going to remain constant, but the volume is going to fluctuate. How much the volume is going to fluctuate will depend on the compressibility of the system. So if you measure the volume fluctuations, you're going to get the compressibility of the system, right? If you do an NPT simulation of a liquid, If you measure the volume fluctuations, then you're going to get the compressibility at the constant temperature. So thermodynamics treats these response functions slightly differently. Statistical mechanics treats them slightly differently, right? All of these are basically Hamiltonian dynamics, right? So essentially, what you have is an extended Hamiltonian. And in this extended Hamiltonian, for example, if I want to implement an NVE, I do not need an extended Hamiltonian. It's simply solve the Hamilton's equation of motion. The initial condition will specify the energy of the system, and that should remain constant. So you have to choose the density in such a way that it's a stable equilibrium point. If you choose the volume in if you choose the volume in such a way that it's an unstable equilibrium, then of course you're not going to be able to equilibrate the system. But if you choose an NPH, we'll come to it later on, then of course it's slightly more trickier. And the problem here is now you have a thermostat as well as a barostat. So that means that you are going for an extended Hamiltonian where you can write a Hamiltonian for the thermostat as well as the barostat. So what follows is a set of equation which is in literature is known as the Nose-Hoover thermostat and barostat. So you can turn off the thermostat or the barostat however way you want to do it. All of this of course preserves the momentum because it's a Hamiltonian dynamics, therefore momentum is preserved even at the coarse microscopic level. So there is no dissipation that is encoded in these equations, right? What happens in a dissipative dynamics? It's extremely coarse-grained. DPD, if you take for a DPD, which is dissipative particle dynamics, basically in a DPD, you do not have an explicit solvent. You basically have a big colloidal particle, which is immersed in a point-like, I mean, the solvent is modeled like a point-like particles, right? And accordingly, you just take care of the hydrodynamics. There is implicit solvent. Langevin dynamics is also dissipative dynamics where you do not preserve momentum. So situations where you want momentum to be preserved, you will not use this kind of a system. Except dissipative, I mean except DPD or MPCD, multi-particle collision dynamics, where you by hand ensure that the hydrodynamics is preserved. Because the momentum conservation actually is related, is tied to the hydrodynamic equations, right? Okay. Why is it not moving anymore? Acha. Now comes the basic fundamental question that what are we interested in? And some of these are there. I mean, what you see over here is one part is statics and one part is dynamics. In statics, typically we are interested in equation of a state. Whether you take a simple liquid, whether you take a complex fluid or not, I mean, what would be the equation of a state, right? I mean, pressure as a function of rho and T. That's one of the equation of states that we are looking at. And so this is the more general expression where Fi is a generalized force and Xi is a generalized coordinate, and I have the temperature. So here, for example, for a simple fluid, pressure will be a function of the chemical potential and the temperature. There can be other quantities also. If there is a phase transition in the system, we have to characterize the phase transition. What kind of a phase transition there is, right? Is it, for example, it's a liquid-gas transition, or is it, demixing of two types of solvents, right? So you identify the critical points. Usually what happens is associated with this phase transition is also a correlation length. Now all these are static quantities. There is no dynamics which is involved over here, right? The problem with the critical point is you want to stay as far as away from the critical point. But of course, we need to study that, right? The critical point actually keeps the problem. There are ways out of it, but we'll see. The other kind of thing is that what you measure are the response functions that we are talking about, the susceptibility, and essentially that you measure from the fluctuations. Right? So this is one part of it which we traditionally call the statics of the system. The other part comes the dynamics. Right? And this, any time scale will always scale as some length scale to the power z. And the models that you choose, the kind of an ensemble that you choose, will determine the value of z. So this is, for example, if you look at a dynamic structure, basically if you take the density modes and if you correlate them together, you get the dynamic structure factor, or what is called the intermediate scattering function. Right? Now every mode is going to relax. Typically it relaxes exponentially. Right? And this relaxation time, again, as you approach criticality, this relaxation time is going to be longer and longer. This relaxation time, corresponding to the largest wavelength mode that you have in the system, will determine your equilibration time. Right? And you see that if this goes, for example, Z is typically for a fluid, simple fluid, or even for a binary fluid, Z is typically of the order of 2. And once you have L square, so if the correlation length goes one order of magnitude, your time scale goes 2 orders of magnitude. So that difficulty is always there. So one has to be smart when implementing such things. The other, of course, is the temporal correlation. Intermediate scattering function is one of them, but you can define physical observables in your system which are otherwise, which can be experimentally accessible or may not be experimentally accessible. That's the advantage of MD simulations. And you can correlate them and you can figure out how it decays and so on and so forth, and what information. The most important thing is analyzing the data. What information can you get from that? The transport properties, diffusivity, viscosity, mean square displacement, heat conductivity, all of these are transport properties. Now, these are slightly out of equilibrium simulations. So if you want to measure the viscosity, you have to create a velocity gradient. Now, that velocity gradient can be created in several possible ways. You can artificially put in a velocity gradient and measure the shear and the strain and the stress. Heat conductivity, you have to put a temperature. But these are all out of equilibrium simulations. Fortunately, this is where linear response comes. Linear response comes, and linear response tells you that all of this thermal conductivity, viscosity, diffusivity, essentially, I can write it down as correlation functions of the equilibrium correlation functions of the respective fluxes. Right? So, for example, I can use the green cube. I can figure out the diffusivity from the green cube using the velocity-velocity correlation. Right? I can figure out the viscosity from the shear stress correlation. So this is what is again going beyond the equilibrium simulations. Now, we'll come back to it. Not too much. Again, I mean, this is too short a time to discuss everything, but we'll give you a general overview of what it is.
So, just a short question here. When you're talking, can you go back to the slide where you're using this relaxation rates depending on the L power Z, and Z is different for different type of enzymes we choose?
That's a good question. So we will see in a moment when I show you some examples of it. For example, when you study fluid dynamics, right? If you choose an NVE or an NVT, the Z changes. So it's well known that
is there any short answer for that? How it actually changes?
It depends on the conserved parameters in the system. How the conserved parameters couple. So the more complex the system, the more difficult, more involved is the analysis.
You usually have only two parameters in the system. It could be momentum or something.
Not necessarily. If you have two types of fluids, then you also have the concentration, which also remains a conserved parameter in the system. So there's a density, there's a number density. And then if you have NVT, Z is typically 2. If you do it NVE, Z is roughly of the order of 3. So it's 3 plus x times eta. X eta is the universal exponent of the viscosity diverges, determining how the viscosity diverges near the critical point. So Onuki is a very good book to read it up.
Sorry?
Onuki is is a very, very good book to read. This is typically a figure. This is a nice illustration which I have taken from Professor Praval Maiti's lecture, and it tells you that where MD stands. So this is a continuum that in terms of time scale and length scales. This is the continuum that we are looking at, and this is where we are. Below this we have quantum mechanics, right? And just above this is we have a mesoscale dynamics, right? This is again a figure from Allen. It's taken from Michael Allen's Computational Soft Matter. It's Introduction to Molecular Dynamics, and it illustrates how this molecular dynamics is so useful, right? Because what happens is, what experiments measure is something which is an observable, right? But for that certain event or observable to behave in a certain way, there's a lot of microscopic things that happen which the experiments cannot measure. They may not have the time resolution, they may not have the spatial resolution. But those are the things which simulations can probe. And that is the biggest advantage. So basically, there are several ways of, this is, as I said, this is the part where you look at the phase diagram, you look at the structure, and then you look at the dynamics. All of these are accessible in the simulations. In fact, one can even go beyond that and ask more fundamental or microscopic questions which are otherwise inaccessible to an experimentalist, right? So the real system is a complex fluid. You can make a model. You can model that complex fluid in your simulation. You can simulate it and then test your theory with the experimental result, simulation result, and the theoretical predictions. All of this combined is then going to give you a better understanding of what is happening, what physics is going on in the system. This is the typical schematics of how MD runs. So you first initialize the coordinates and the momentum. Now here the idea is that when you initialize the coordinates, you just don't put in randomly particles in the box. So if it's a very dilute system, you can do that. But after some point of time, it's going to just, your first integration step, it's going to just diverge because it comes too close to each other. So you start with a periodic lattice. It can be FCC, it can be BCC, your choice. Once you have that and you choose the momentum from the velocities from the, given the temperature, you have fixed the temperature, and from the Boltzmann distribution, you start initialize the momentum. This is the bottleneck. This is where you build the neighbor list. So typically in a simulation, I have not shown it here, but in a simulation, what we have is always a short range force field. Long range is more difficult to handle. Electrostatic is one example of this, and the second example is the hydrodynamic interaction. So these two are very difficult to handle. So most likely, in almost all cases, we look at short range interaction potentials, Lennard-Jones, UCA, whatever you take, these are all short range. By definition of a short range, therefore, you mean that there is a cutoff distance, beyond which you are not interested in the potential at all, right? And if there is a cutoff distance, therefore, you have to know who all are lying in that cutoff distance, and that's a job that is done by the neighbor list, right? So once you have built the neighbor list, and this is the bottleneck, then comes the forces. You know the potential, you calculate the forces. This is not such a, rest of it is not such a problematic thing. Then you integrate the equations of motions. This is also where you have to be very, very careful about. You apply the boundary conditions. So typically we have a periodic boundary conditions. I think all of you know, all of you have done simulations before, right? So, no? Okay. So basically what you say is that your simulation box is just a tiny, tiny volume in the actual system. So particles moving in from this side of the boundary are going to come out from the other side. Corners are the ones which are a little bit tricky, but with a little care, you can also take care of that, right? This is where you output the statistics, but you have to wait a long time. I mean, not a long time, but a significant, equilibration time until the system has equilibrated from your initial lattice phase to the thermodynamic state that you want it to be. After that, you measure statistics. And the amount of equilibration time will always depend on the typical correlation time in the system. So you can look at the density-density correlation, you can look at the order parameter correlation and see how big is the correlation time. 10 times that correlation time is typically the equilibration time. You always have to be careful, right? And you keep on doing this until you are satisfied with the quality of the data that you have. So as I said, the most expensive part of the simulation is the neighbor list calculation. The brute force calculation is like you take each particle, run over all the particles, right? So that's an n square operation. So you want to optimize that. So if you take n square, I mean, if it's 10 to the power 3, then you realize that it's 10 to the power 6 operations. It's extremely expensive, right? More efficient is what is called a cell list algorithm. So you break the system, we'll show it in a little bit. Now your hardware architecture can also allow other algorithms. For example, if you're doing it in a GPU, you can also have a 2D algorithm to up to 10,000 particles, you can very efficiently implement a 2D algorithm for neighbor list, right? This brute force thing you pick up, but you implement in a 2D fashion. I'll illustrate in a bit. Now this is a cell list. Basically, these are the cells which have been shown for the periodic boundary conditions, but the idea is very, very simple. You have a cutoff distance, and on top of it, if you want to efficiently implement it fast, then essentially you add a skin length to that. So whenever two particles move together a distance greater than equal to the skin length, you update the neighbor list. Otherwise, all of them are lying in the cutoff volume, right? You divide the systems in volumes, small sub-volumes of the size of the cutoff length. And then you figure out which particles are lying in this volume. And for a given volume or container, there are 9 such, you have the surrounding containers. From this, you figure out the neighbor list. So at any instance of time, you don't have to loop over all the particles, but only this finite sub-volume of the system. So this algorithm is very, very efficient, and how you implement it is also efficient, right? Now, the other one that I was saying is, for example, in a GPU, typically a block and a thread structure is like this. A GPU basically is a parallel architecture where you do the simulations. Now, every grid will have threads like this. Each of these threads is responsible for one particle, updating the coordinates and momenta. So when you are going to do a neighbor list, instead of 2 for loops in a sequential fashion, when you loop over all the particles, in fact, you can have the particle coordinates loaded here along this direction as well as along this direction. So all you have to do is this grid has to only go over, let's say, 256 threads in this block. This one only has to go over 256. Now this is slightly memory extensive in the sense that every block must have its own neighbor list. And you flatten or coalesce the neighbor list only after you have done the neighbor list calculations, right? So that's why going beyond 10,000 is slightly tricky, because you also, in this architecture, you also use the shared memory, which is, the modern GPUs have a slightly larger shared memory, so you can maybe go up to 100,000 or no, 20,000, 30,000 particles, but typically older generation GPUs beyond 10,000 it's slightly difficult to go. The other thing is also most important. If possible, you use a Hilbert space sorting algorithm. Now, this Hilbert space thing is known to mathematicians for a long, long time. It's recent application in molecular dynamics is very, very recent. So what is it that you do? See, when you have started the simulation, you have just put all the particles coordinates in one array, right? But these particle coordinates are going to move. These particles are going to move around, and therefore it is not initially, when you first started off, they were placed in the memory according to their physical location in the physical domain. But then they move around, right? All the way they move around. So therefore, a neighbor list, you have to search a longer part of the memory. It is better to sort the particles based on the distance, so that physically if they are in one compact domain, then they are also in a close in the memory. So then the search in the memory algorithm in the memory is quicker. Otherwise, you have to figure, I mean, when you do the physical search in the hardware, then you have to go from one physical location of this memory and the other particle might be located at the other end of the memory block. So that takes time. If it was just immediately in the neighborhood, then it's faster access. Very quickly you can do that. So that actually speeds up the whole neighbor list calculation process. Now let's go for choice of ensembles. As I said, that depends on the conserved quantities in the system. I have microcanonical ensembles, NVE or NPH, and canonical ensembles, NVT or NPT. These set of equations are what are called Nosy-Uver, barostat, and thermostat. You see, this alpha is the one which is responsible for the pressure fluctuation, maintaining the pressure, and this gamma is the one which is responsible for maintaining the temperature. The other type of thermostat, which is also very frequently used, but at a very, very coarse-grained level, and in this picture, there is no explicit solvent. There is only an implicit solvent, and that implicit solvent comes out through this Langevin, I mean, this random noise. This is a Langevin thermostat, right? For statics, either of the setup is okay, should not matter. It should give you the same critical temperature, because the system doesn't care about what kind of a thermostat you have chosen, right? I mean, system, your critical temperature should come out to be correct. The dynamics is different. Dynamics matters on what kind of an ensemble you have chosen, right? Now comes the next part where you have to be really, really careful in choosing things, is the integrator, right? And there are certain things that you have to be very careful is simplicity. How long does it take to code that integrator and how easy it is to debug? How fast then is the efficiency? How fast to advance a given system? For example, if you want to take the system from one step to the other step, if it involves 10 steps in your integrator, then that's not a very efficient algorithm. So you search for an algorithm which will probably take you to in 3 steps, do the job in 3 steps. Then you save time in your computation, right? Stability is very, very important, particularly in systems which are where you need long equilibration times in a glass or in systems which are very close to criticality, right? There you need long equilibration time because the error is always going to propagate. So when you do the simulations, you have to measure the energy, you have to measure the temperature, you have to see the momentum, whether you have a net drift which comes in the system just because of the error. If you see such a drift, there are only 2 possible ways. You have to reduce the time step, increasing the runtime, or you choose a better integrator where the stability is much better. Reliability, it can handle a variety of temperature, densities, and potentials. So if you change the potential, depth, width, whatever you do, it can still do it. There is no divergence that comes in the integrator. And the last one is the vectorization. So that means that your integrator should be such that if you want to parallelize it, you can do it very easily, right? So these are these are done. There are several choices. The other thing that you must also remember is that time reversal symmetry must be preserved when you are discretizing the equations of motion, right? Velocity Verlet integrations, oh, this is slightly wrong because that the other one has to be h4. This is, the error is of the order of h4, this is of the order of h square. So these are the 2 integrators, they are identical. They are identical. I mean, one can go from velocity Verlet to leapfrog as well as from leapfrog to velocity Verlet, but they are very, very stable integrators. Then you have random forces. The Langevin thermostat, when you implement that, you have to keep it in mind that when the moment you use fluctuating forces, the error is of the order of square root of delta t, square root of your discrete time step that you have chosen. Okay, I have to, this is a velocity Verlet scheme, right? You have this data at this instant of time. This is the one which is at previous instant of time, right? What you first do is you update the position. You update the position using the position at t n minus 1, the momentum at Tn, and the forces, the acceleration, the forces at Tn. Once you have done this, you update the forces at Tn plus 1. And using this, then you update the velocity. Using these 2, you update the velocity. This is a velocity Worley. You can also have a very simple version of that, which treats the position very nicely. It's called the position Worley. The other one is very, very simple and possibly better to implement also, easier to implement, is what is called the leapfrog. Now, there you do not have V of t, but you always have V of t plus h by 2 and V of, this is V of t plus h by 2 and V of t minus h by 2. You always have this, right? So, from the position you calculate the forces, and from these two, V of t h minus 2 and the forces, you calculate V of t plus h by 2, and in the next step, you update the position, right? I'm going to skip the next slide because that explicitly, this is an explicit illustration of how you discretize, and it obeys the time reversal symmetry. The other integrators that are available is the Runge-Kutta, but that's RK4, that's even more complex. For most of our applications, we do not require Runge-Kutta. Velocity World is good enough to give you that. Now let's talk about large-scale parallel simulations. So this is something which is what last 15 years. So last 15 years, this has been extremely popular. This is a very, very efficient parallel simulating architecture, right? So instead of sequential instructions that you give single instruction to multiple data. It follows the SIMD model. Right? You have several memories so the global memory, and this is already what I have talked about, is a shared memory. So if you look at the hardware architecture, the global memory is slightly far away, slightly away from the processor, whereas the shared memory is on the processor itself. So it's like a cache memory, right? A very, very small. I mean, the older generation cards used to have 4 KB or something like that. I don't remember now. But so you only can possibly load, if you are using 3 coordinates, only a part of the array in that shared memory. But that access is very fast, right? There are other ways also to do that. So the structure is basically this: the global memory, there's a constant memory which is accessible from the host. The host is your CPU, the C compiler basically. So the C you program it in C, the C hands over the execution to GPU whenever it encounters a kernel, right? This is what you have, and you call up, for example, update particle coordinates, right? This is a kernel that you call. And this is a host, it's written in a host C function. And the moment it encounters this this call to a device function, basically it hands over the operation to the GPU, and then again it comes back, the control comes back to the host. So these back and forth happens. The less number of back and forths if you have, the better for you. But sometimes if you are doing a very costly statistics, it's unavoidable, but what can you do? I mean, it's unavoidable. So you have a global memory in a device. I mean, the GPU, you have a global memory, you have a constant memory, and then you have a shared memory. There is also a part of the global memory is also slightly kept what is called as a texture. So GPUs have a history is that this is the same card that you used to play games. And then it was seriously developed for scientific computation, because the games one, they don't have the standards for scientific computation. So you have to trust the numerical result that is coming out of your computer, right? Now, I'll just briefly, I think I have roughly 25 minutes to do. So this is what is critical phenomena, right? That's what we are talking about. And this is from my work. Essentially, you look at it, then there are 2 types of particles here, white and blue. Above the critical temperature, this is in a mixed phase. If you keep on going down the temperature, it demixes to a different phase. I mean, you have a clear demixing of the 2 liquids, right? So this is mixing, demixing transition. I think the transition point is the consolute point. That's what it's called. So it will have the normal liquid vapor transition, but this is a separate transition. So in order to study this, you have to be in the high density regime. If you go, let's say, if you do take the density too low, then you are going to hit the liquid vapor transition before you hit this point. So you typically densities here, for example, the density has been set of the order of 1, right? Now, critical singularity in the response function, the susceptibility will diverge. The small epsilon is the T minus Tc, right? And the specific heat also diverges. the correlation length diverges and the time scales also diverges with the length scales. This is how the static structure factor, the inverse of it has been plotted. This is the theoretical prediction of it, and you can see those solid lines are the plots from the theory. This gives you a measure of the correlation function. Right? So this gives you a measure of the correlation function. See, the idea is that wherever you have an analytical result present, you should rather fit your data to that analytical result rather than fitting to any arbitrary functions. Then the number, it's always better to have less number of fit parameters in your data. I mean, with 14 fit parameters, you can probably fit an elephant, right? So that you don't want to do that. You want to be true to the physics that is there. So if you have an analytical expression, for example, here, the only two fit parameters are the susceptibility and the correlation length. Susceptibility can also be measured from the concentration fluctuation. So you have another independent way of measuring the susceptibility. So then you compare the two results. Preferably, you will measure the susceptibility from the concentration fluctuations. So then the correlation length will come out accurately, right? So the choice of ensemble is microcanonical here. So you equilibrate the system in NVT because you want a particular temperature, the system to be at a particular thermodynamic state at a particular temperature. So you equilibrate the system at a particular temperature and then you switch off the thermostat. So you use the same Nosy-Hoover thermostat, but except the barostat is now turned off. There is no alpha. You switch on the thermostat and then you equilibrate the system until you have the temperature has stabilized, the system, everything has equilibrated. Then you switch off the thermostat. Then you let the system, then it's an NVE ensemble. Then you wait for some more time. If there are any transient effects that have arisen because of switching off the thermostat, they will die out by that time. And then you start measuring the data. Now, momentum is conserved here because momentum is also one of the conserved parameters when you look at the continuum theory for this. But as I said that near criticality, if I want to measure the critical temperature, so on and so forth, there are several ways. Binder cumulant is one of the ways. Look at the correlation length, look at the susceptibility, and you can see that it's going to diverge. You plot them in a log-logs plot. You know the universal exponent, and then from that fit, your TC is going to be the fit. The amplitude of the correlation length is going to be a fit. Do I have it here? Yeah, so this quantity is going to be one of your fit parameters if you are plotting the correlation length as a function of time. And here, TC is going to be one of your fit parameters. So that's going to give you roughly an idea of a TC. But the Binder cumulant serves to be a more accurate estimation of a TC. Binder cumulant is just looking at the order parameter and calculating the non-Gaussian quantity, right? What is called the kurtosis. In statistics, it's called the kurtosis, right? But there are other ways also, and that's where the finite size scaling comes extremely handy. So what you do is, you take the same set of simulations, you divide the systems. Now, typically if you want to determine the statics, you will do a Monte Carlo. That's a standard thing, you always do a Monte Carlo, right? But then if you want to do the dynamics, you have to do the molecular dynamics again. So rather if there is a way to figure out both in one go, and this is one of the useful tools in molecular simulations is a finite size scaling. So you divide the system into smaller subsystems and you measure the order parameter there. Oh, I have removed that slide, but nevertheless, so you measure the order parameter there, and these are open systems now. You try to avoid the systems which are at the boundary because they are affected by the periodic boundary conditions. You only take the systems which are core inside. And then there are the finite size scaling results for the order parameter fluctuations are there. So you can plot it, and from there you can, for the susceptibility it's also there. From there you can actually figure out the critical temperature very accurately, right? The other part, of course, from the same set of simulation is to extract the dynamic the dynamic quantities. So what basically you look at is you look at the time dependent structure factor and the relaxation times for those Fourier modes. So what we call as tau q, that's the one which is basically over here. Now, if you are far away from this, then you expect that the dynamics is diffusive. It's a diffusive dynamics, right? So if you can consider a blob of correlation length psi that moves around the system diffusively. And that is exactly what you see over here. But near criticality, this changes. Near criticality, this changes. So it goes to 1 by k cube scaling. So it's like you have a mode dependent diffusivity now, right? But most importantly, all of this data is extracted from the same set of simulations. We did not do a separate Monte Carlo to extract the data. Now we are interested again. So again, what we are looking at is a phase transition in a 2D colloidal system. But now I'm not going to use a Nose-Hoover thermostat. I'm just going to use the Langevin thermostat, because momentum is no longer a conserved quantity here. It's a 2D system. The phase transition happens in a different mechanism. It's a defect mediated phase transition. So essentially you find 3 phases: solid, hexatic and liquid, and the solid has a quasi long range order. 2D cannot support a true long range order. The hexatic will have a long range order. So in the solid phase, the solid order correlation decays as a power law. The orientational order correlation does not decay. It's just flat far away. Asymptotically, it's just a constant. In a hexatic phase, now it turns around. The solid order will always show a short decay, which means that you have no positional order. You only have orientational order in the system, which is the bond order basically that you see. The orientational order will show a power law decay. That means that it's a quasi long range order. It's not true order, but it's quasi long range. Ensemble of choice was a canonical NVT with Langevin thermostat as the choice of thermostat. No longer Nose-Hoover. I'm not interested because it's computationally expensive. What I have is essentially a system of colloids which are immersed in a solvent. In the earlier case, I had an explicit solvent in whose phase transition I was interested in. But now I have a slightly bigger particles which are immersed in a solvent. So I'm no longer interested in the hydrodynamics, because I know that for many particle system in statics, hydrodynamics rarely plays a role. Dynamics, yes. And this is the kind of data that we got. So essentially you define the Fourier mode as e to the power I q dot Ri. Ri is your particle position, right? So you pick up a wave vector, q value, and you define rho q as this. The structure factor, the static structure factor is defined here as rho q, rho of minus q. Because you have translational symmetry in the system, therefore q must always couple with minus q. And in a solid, what will happen is you will see this peaks. This is like an X-ray diffraction experiment. And as you go, as you keep on, see, it's a very high density, 0.922. As you keep on decreasing the density, you will see that this peaks, they slightly diffuse. And then comes this, where peaks are slightly visible, but now they have elongated along they have been stretched along the ring. This is a hexatic phase. And then as you further go down, it goes to an isotropic liquid phase. This phase has the highest symmetry, and this phase has the lowest symmetry. Right? If you plot the g of xy, then you will see that in the solid phase, this is both the cases. Essentially, you will see that you very nicely see such correlation. The difference between these two is they're very closely, but if you go beyond this, the picture becomes very hazy or blurry. That means the correlation is very, very sharp locally. Far away, there is not much of a correlation. And if you look at the phase diagram, this is one of the things that we are talking about. The first thing is to look at the pressure density. And a behavior like this will tell you that there is a signature of a first order phase transition, right? And there are ways to figure out the first order phase transition. You measure, you basically do a Maxwell's construction here, look at the area that gives you an estimate of the free energy. And that free energy must decay in a certain fashion if it's a first order phase transition. Now, this is the microscopic information that I was talking about. See, this is a spatially resolved orientational order, which is not accessible in the simulations, in the experiments. The experimentalist will show you that the structure factor is accessible to them. To some extent, not to some extent, the pair correlation function g of xy is accessible to them. But the orientational order has to be figured out. But this is very, very easily accessible in the simulations, the local orientational order. So you can either attach an orientational parameter order with the particle, or you can coarse grain the system into smaller subsystems and calculate the orientational order locally. And then once you have calculated the local orientational order, you can also correlate it and figure out how does the correlation decay in this case. Right. So these are all the things that you can do. The next example is hydrodynamics, right? Now here the illustration is basically I have a big particle which is immersed in a small bath of fluid particles. And so it's a colloid. The actual system is a colloid which is moving in a liquid, right? Let me just, these are all well-known things. I mean, we have seen them n number of times in our lives. This is a Langevin description of it, and I have the Stokes-Einstein relation, the velocity autocorrelation function in the Langevin description tells me that it's going to decay exponentially at all times, but this is not true. So what you have in the velocity autocorrelation function is the power law decay at late times, and this power law decay solely comes in because of the flow that you have, because of the hydrodynamic, because of the backflow, because the particle has to move forward. In order to move forward, it has to push the liquid. Now the liquid circles back and gives the feedback to the particle. It's this circling back, it's a vorticity which you have created over here that is going to give you a power law decay in the velocity autocorrelation function. In this simulation, one has to be very, very careful. You have to resolve timescales of the order from this to all the way up to this. Right? So you have to, your simulation has to be very, very efficient. We are talking about almost like 10 to the power 8 time steps in the simulation. This is the production run. Before that, you have an equilibration run, which is of the order of 10 to the power 7. So you can imagine the runtime of your code. So if your code is very poorly written, if it is not properly written, efficiently written, then it becomes extremely, then it's just a mess for you. So you have to put in all the tricks of the trade in your code to ensure that your simulation runs within a reasonable period of time. I mean, 3 months is for one is not a reasonable period of time, possibly 3 days, right? Now, it also illustrates some of the characteristic timescale. This is the one that we are talking about, the vorticity diffusion time. It's typically determined by the viscosity of the solvent. This is the inertia part. So this is the particle inertia is going to determine a time scale. The friction and the particle inertia is going to determine this. And then, of course, you have the colloid diffusion time, which is determined by the diffusivity, right? I want momentum to be preserved here, because otherwise I'll not get the power law decay. I will not preserve, if I don't at the micro scale, if I don't preserve the momentum, don't conserve the momentum, then hydrodynamics will not be, hydrodynamic laws will not be obeyed, because hydrodynamics is just a coarse graining of the microscopic picture, right? So if the underlying Hamiltonian dynamics is not hydrodynamics, sorry, underlying dynamics is not Hamiltonian, I will never have hydrodynamical equation of motion in the system. So here, of course, I choose the Nose-Hoover thermostat because it's more close to the experimentally realizable, where it's the system, you put a particle in a water and it's an open system, it's connected to the atmosphere, so the pressure actually remains constant. Most of the experiments you see, pressure is the one which is it's under constant pressure. Okay, we have already seen those equations. Now this is an illustration. So you see, this is a power law decay. Your Langevin, this is an exponential decay, and your Langevin equation would have said that it would have decayed like this way. But in reality, it doesn't do that. Adler and Wainwright were the first ones to show this, long time back. What is interesting here is now I can measure the friction coefficient on the particle and the fluctuation dissipation. In such cases where I have a spatial-temporal correlation in the system, you move away from the Markovian description of the Langevin to the generalized non-Markovian description of the Langevin of the colloid, right? And when I have a generalized Langevin equation, basically the friction term, which is gamma v, is now replaced by an integral gamma v minus t minus t prime v t prime. This is again the linear response thing that we are talking about. It just arises from the linear response, the most general linear response. Now, consequently, the friction, the Stokes friction that we have studied is only the steady state friction, which is in the limit of omega to 0, right? So you have actually in reality a frequency dependent friction. And this is The experimental work which was published in Franoche in 2011, these are results from the simulation. So if you measure the power spectral density of the thermal forces, the fluctuating forces, right, then actually this is the part you see which is identical to that. It's because this is the compressible part. This is where the fluid is, sorry, incompressible part. This is where the fluid is incompressible. And the knee that you see over here is the sound mode. This is where the sound mode comes in. And this is the part which is the compressible part of the system. So any fluid is just not viscous. It is actually viscoelastic. So what is the difference? It's like a spring and a dashpot. So if you give an impulse, right, you expect that, if you expect that impulse to decay out, to be dissipated immediately, that doesn't happen, right? If that impulse is at very high frequency, then the medium surrounding it behaves elastically. So it's like, it's going to deform like you have a motion in a solid, a colloidal Brownian motion in a solid. Surrounding solid is going to deform, you're going to create the shears, strains, and so on and so forth. Only when you wait for a long time, that's omega to 0 limit, then you will see that slowly the particle has moved, and all the deformations, all the stresses that it has created has slowly dissipated in the system. So now the question is, why can't we see that? Water is pretty much incompressible. It's just that it has a very small, compressibility, so that you have to go at very high frequencies to figure out, to see the effect of compressibility. Okay, 10 more minutes. Last part, this is, I just put a slide, I do not, it requires some more things. So, non-equilibrium system. So, they are characterized by a particle current or a heat current, and therefore an entropy production in the system. Now, example, driven diffusive system, active and passive phoresis. Both of these are non-equilibrium systems. You have to be extremely careful when you are applying a gradient to the system. There are lots of things which can go wrong. You can introduce an unnecessary drift in the center of momentum, so that the whole system starts to shift, and that you realize is something of a physical effect. Please be very, very careful about that. So temperature gradient you create either by a Nose-Hoover thermostat locally. You identify two slabs at the boundary, and you only apply the thermostat there, remove the thermostat in between. Or you can do a velocity rescaling, but with a momentum conservation. In the sense, the center of mass momentum, relative to the center of mass, you do the velocity rescaling, not arbitrarily, right? Momentum gradient, of course, you can do a velocity rescaling. Again, with relative to the center of mass, you will create a gradient. You can also do a Muller-Plathe algorithm, where you basically you switch faster moving particles to one side, slower moving particles to other side, and then you automatically create a gradient. So this is going to give you the viscosity, this is going to give you the thermal conductivity of the system, the results of these simulations. Now the chemical potential is something which is extremely difficult to carry out in a molecular dynamics. It is typically done in a Monte Carlo. Chemical potential means that you have the amount of work that you do to put in one additional particle, and that is extremely difficult. Now this is the last example I'm going to talk about. This is a directed motion. This is actually self-diffusive thermophoretic particle that you see. It's a snapshot from the simulation. This is a genus particle which has been modeled like a genus particle. This side is gold, this side is polystyrene, different colors. It's a very, very small particle in the simulation. So basically, if you heat one side, the other side automatically gets heated up, right, irrespective of that. So what happens here is, what happens inside the particle is not very important. What happens outside in the fluid is very, very important, because the motion, the self-diffuse thermophoretic motion, the directed motion that it generates is actually dictated by the hydrodynamics of the system. So this is the schematic, and if you start measuring the temperature profile, essentially what we did was we tried to measure the radial temperature profile, and you will see that there is a discontinuous jump of temperature at the interface. And this because there's two different impedances. Sound modes travel with two different speeds, right? So therefore, what you have is a Kapitsa resistance here. Now we exploit this, and what we do here is that this Kapitsa resistance is actually, we modify the Lennard-Jones potential and say that this is a weightability parameter. If you set it to 2, then two small particles are touching each other. If you set it to 1, then they are not touching each other, but they are slightly far. the minimum distance is 2 to the power 1 by 6 sigma. If you set it to 1. If you set it to 2, then their minimum distance is 1. Sigma, right? So this drop in temperature, if you set it to 2, then becomes very, very small. If you set it to 1 or even to 0, then it becomes very, very large. 0 means there is not much cross-talking with the liquid. So there is no attractive part of the potential. It's just purely repulsive. So therefore, the solid is repelling the fluid. So there is no, there's a less propagation of the heat from the solid to the liquid. What you do over here, once you choose different, so in this case, you choose different weightability parameters for the two surfaces. And once you have that, you see it's a slightly different way of plotting. This is T of r theta. This is the polar. So you put the symmetry axis like this, your theta goes all the way from here to here. And r, of course, goes from the center to all the way far away. But this is the surface, and you see there is a temperature gradient which you have created. So here it is very hot, here it is very cold, which means if you start measuring the temperature as a function of theta, this goes down like this way. So hot here and cold there. This is how it looks for different choices, right? And you can expand the T of r theta in terms of the Legendre polynomials, right? And this is how the 2D map, heat map looks like, right? Now, what I'm interested in, which is not accessible in the experiment, is the slip velocity. So essentially what happens in diffusophoric motion is that you create a tangential stress. Now, you also create a normal stress, but the normal stress is balanced by the forces because the force is radial, right? So the normal is balanced by the your interaction forces, right? So your pressure is going to change. Particles are going to slightly move apart, right? They will readjust. But there is no tangential force. The interaction is not tangential. So this tangential stress remains unbalanced. And when you have a tangential stress which is remaining unbalanced, it's going to create a flow. So the fluid moves like this way. And if you have to preserve conserve the momentum, the particle must move like that way. So that's how the diffusophoretic motion happens. That's the basic idea of any diffusophoretic or any kind of a self-phoretic motion. These are all taken from Bickel, Maggi, and Verga. So these are typically the flow field. Now this slip layer is a boundary layer, which means that this additional stress, this flow that you have created, is only near the surface. It doesn't go all the way to the boundary of the solvent, right? So the idea was that can we access that in the situation? So basically what we do here is we take this particle, we take different shell thickness. Now this is the advantage. The reason I wanted to show you this is because I can do it in the simulations, but I cannot do it in the experiments. The slip velocity in the experiments is extremely difficult to measure. I can measure the directed velocity that the particle gets. So what I do here is I take this particle, heated particle, the genus 1, and I look at is a fluid layer over which the velocity is averaged. I will change my S, right? Do I have? Yeah. So this is u of s theta as a function of theta. Now I keep on changing s, right? So the first one is 0.5 sigma, this is 1 sigma, then this is 2 sigma. So your statistics become good and you sort of start to see that there is a trend, right? And this is how exactly the microscopic picture looks like, the flow field. So you measure the slip layer, and as it turns out, I have to go back slightly. Okay, my time is almost up. Yeah, you see, the second is this coefficient which determines the slip velocity. Because what happens is the gradient of this temperature gives you the normal stresses, the tangential stresses. The tangential stresses will depend on the gradient of this temperature, and the velocity is going to be dependent on that. So these coefficients will determine that, in particular B1. So what we do is here that for different values of B1, we plot it, and we see that for both active and passive cases, you see passive cases, in both the cases, there is not much dependence on S. S is again the layer that you are talking about. But for active cases, there is a dependence. And typically, it turns out that the slip layer, I don't know whether, can you see the gradient here? There is a slightly grayish gradient to white, gray to white gradient here, and that gradient disappears at 2.5 sigma, typically of the order of the interaction range. So if you take a potential which is slightly long ranged, you're going to generate more kind of a directed motion. But your experiments, I mean your simulation is going to be more complex, more computationally expensive, right? So these are some of the current explorations. This is a movie where we have a 2-layer vesicle and a shear. And this is still in its nascent stage. So Nitish is not here. Nitish is actually doing all these things. And it's interesting that this is a very, very small shear rate, right? And you keep on changing the what you change is the rigidity of the ring, right? So this is same thing, but now I'm going to ask a different question. So the reason I want to show you here is the kind of questions that you ask. Now I have a bilayer, right? So both the layers are tied to each other by an interaction. So as they move around, so it's a catch bond mechanism, right? They are going to slip. So one bond is going to break, the other bond is going to form. So what is the lifetime of this bond break? So all these questions you can ask, and they're very, very interesting. I mean, but you have to look at the system and figure out what kind of questions you want to ask, right? But these are not very easily accessible in the experiments. Again, the last one is this, and this is basically I compress. I want to figure out where it breaks. So you see this is goes to a hexagonal, nice honeycomb structure, and will it show the breaking? No, it doesn't. So at one end, it breaks from the top. So that gives you a sort of idea of how much the compressibility of the system is, what kind of defects. So now it's you are not producing any defect here. Rather, you'll be producing a defect when, if you reduce the density here, then you're going to produce defects here. But as it goes into this honeycomb structure, you're not going to produce a defect, right? Okay, so basically, work has mostly been done by Nitish and Dimpy. Dimpy is already here. These are my collaborators, and this is the cluster, the GPU cluster that we have. And so, thank you, and questions.